Okay, Bismillahirrahmanirrahim. So today we will start our lecture. So let me just share the screen. Okay. So yeah, in our today's lecture, we will learn or we will start from article number 7.4 from the CASA book, and that one is the frequency dependence thing, and the dielectric constant and the dielectric losses. Okay, so we know the dielectric constants, and that one is defined as the symbol epsilon, and in free medium that one is defined as epsilon naught, and which one is equals to 8.854 into 10 to the minus 12. All of you know about these things. Sorry. But whenever we will apply some AC electric field, or if we apply the polarization things, or if we apply something related to the frequency, then there will be not exactly same as before what we have learned in free medium. So look, first of all, we will start from article number 7.4.1. That one is the dielectric losses. So, in case of dielectric losses, the static dielectric constant is an effective polarizations under DC conditions. So that one is the effective things, and we have already learned about the DC dielectric constants. So DC means that one is not depends on frequency, right? But look, in this course, we are just going through the material science or the mechanics of the materials. So here we will learn in details of the motions of the molecules or the effect of the polarizations and the many more things. Okay. Now look, we know different types of polarizations and the effect of different types of polarizations. So whenever we are applying an AC electric field, then we know that in case of two parallel plate capacitors, there will be the accumulation of the charges. And in this case, there will be something known as orientational polarizations, which we have learned in our previous lectures. And look, if the instantaneous induced dipole moment, this dipole moment is defined as P, that was defined as P, and then this P should be equals to alpha d E. So here, this alpha t is the polarizability, and we have also got this equations in our previous lecture. That one is alpha d should be equals to P naught square divided by thrice kt. Okay, so we know this P naught means the polarizations at that means at 0 Kelvin, and this K is the Boltzmann constant, and this T is the temperature. Now look, there are two factors. That one is opposite this immediate alignment of this dipole with the field. That one is the first of all, that one is the thermal excitations, and the second one is the molecules rotated in a viscous medium by the virtue of these interactions of the neighbors. That is the interaction of the two neighbor molecules. Now, we will explain this figure later on whenever we will go through the equation. But initially, I am just giving you some briefing about these things. That one is, if we apply a DC electric field, that one is started from E naught, and in this for this particular time E naught, we will get and the polarizations. That one is a fixed. That one is known as alpha naught T D at 0. That means at for DC conditions E naught. So if we look carefully to this figure, then we will see that this up to that time 0, this one is equals to 0. But whenever we remove the electric field, or from we reduce this electric field from E naught to E, then these polarizations, or this polarization decreases in terms of exponential terms, right? So look, this one is an exponential parameters, and that there is some it requires some times to reduce from this upper positions to this lower position. So this required time is known as this relaxation time, which we have already learned in our previous lectures also. Okay, so we know the formula for the Clausius-Massetti equations, and we have also derived these equations in our previous classes. And here, what we actually need to learn here, that one is this alpha d zero. What does this term mean? This term means the value of this constant alpha d at zero frequency. Okay. Now, if we say the rate of decrease, this rate of decrease equals to, if that one is the peak point is p, then p minus alpha naught e, this alpha d0 multiplied with e. With this rate, that one is decreasing. So we can define this rate of decrease. This rate of decrease equals to delta p divided by delta t. That means the rate of decrease of polarizations with respect to time equals to p minus alpha d e divided by tau, where this tau is defined as the relaxation time. That means the time required to be relaxed, or and also this minus sign means that one is defined as the reduction of the polarizations, nothing else. Okay, so this equation is known as the dipolar relaxation equation. Okay, now we know that, as because this one is an AC signal, so we can define these things E equals to E naught sine omega t, right? That means this one is an AC signal. Now in engineering behavior, we also know that these sinusoidal terms can also be explained in terms of the exponential terms. So we can also write down E equals to E naught exponential j omega t, right? This one is from the Euler's equations, right? Now we can uh, we can put this, if we put this value here, then delta p divided by dp divided by dt should be equals to minus p divided by tau. If we look at the equation 7.24, look, p divided by tau, this minus and this minus makes this one as plus, so that one is alpha d naught divided by tau. Previously, that one was E. If you can remember, that one was E. Now, if we put the value of E equals to E naught exponential j omega t, just we have not done anything except we just put the value E equals to E naught exponential j omega t, right? Now look, I know all of you know about this first order differential equation, integration of this first order differential equation, or the solution of this first order differential equation. Look, if we integrate these things, then we will get the solution as P equals to alpha d omega, where this omega is a frequency dependent thing. Alpha d omega E naught exponential j omega t, right? Now, where this alpha d omega equals to alpha d 0 divided by 1 plus j omega tau. So I know all of you know about these integrations, how to integrate. This E naught terms is a constant terms. So if we integrate the exponential terms, then exponential, we know that e to the power mx equal, if we integrate e to the power mx, then e to the power mx divided by uh, m, right? So if we put the values, then this one should be equals, this one will be the constant part. Okay, so this one is the orientational polarization under AC conditions. Now we can also, so this equation is very important. This equation is very important. That one is the, after that, if we decrease the frequency, that means if we decrease the omega value, then we can say that alpha d omega equals to alpha d 0. If we increase the value of, that means for the low temperature, sorry, for the low frequency, this alpha d omega should be equals to alpha d 0. Or if we say that this one is higher terms, that omega t is in higher terms, or this one is greater than 1, then we can say that this 1 by tau, this 1 by tau is a complex terms, or this one is a complex quantity. So finally we can conclude one thing, that one is the dielectric constants, or the for for the AC signal, these dielectric constants epsilon r, there should be two terms. One is positive terms epsilon r minus j epsilon r double prime. Okay, so now our next next job is to find out this epsilon r values and the minus or the epsilon r double prime values. Okay, so I will show these two parameters from the Boyd professor's lectures. We have already derived this thing. Now uh, look, this one is the molecular behavior of a material. So we are applying a voltage V equals to V naught sine omega t. So if the supply voltage is V naught sine omega t, then the field E should be equals to E naught sine omega t. Similarly, the polarizations. Look, this polarization P equals to P naught sine omega t minus phi. That one is the phase difference. Okay. So this figure 7.13b, that one is the plotting of this epsilon r prime and the epsilon r double prime. Okay. So we will also discuss about these things, this equivalent. We can also write down the equivalence of this parameter. That means this polarizations with a parallel resistor and a parallel capacitor. Okay. Uh, just now let me show the equations from the Boyd professor's lectures. So, we have already discussed about this polarization things. P equals to alpha dE. Then this alignment, there are two conditions. I have already mentioned there will be two conditions. Then the polarizability and the frequency. Look, I have also discussed about this, the change in the field and the why, what is the relationship between this two changing field, this relaxation time, and we have also derived up to this. Now the this one is the phase delay part. Now this complex dielectric constant. Look, from our previous explanations or from our previous knowledge, we know that epsilon r equals to 1 plus n alpha divided by epsilon naught. So epsilon r equals to 1 plus n divided by epsilon naught. Alpha, that alpha d equals to, we know that this alpha d omega equals to alpha d naught divided by 1 plus j omega tau, isn't it? We have just put the value of alpha here. Now, as because this one is a complex part, so we can write down the complex conjugate. We can multiply with the complex conjugate part from both the numerator and also the denominator. So in the denominator, we will have 1 plus j omega tau. That means 1 square plus j. That means omega square tau square. But in the numerator, there will be this complex part. So if we separate these two parts, then we will find epsilon r equals to one real part and another imaginary part. So what is the value of this real part, epsilon r? So epsilon r prime should be equals to 1 plus this real part, and this imaginary part means epsilon r double prime. That one is the part related to this one. I think this one should be clear. Now, if we put the value, if we just want to plot these things in a graph with respect to tau, that means sorry 1 by tau, then the graph of epsilon r double prime and epsilon r single prime should be looks like this. Okay. Now the next one is the lossless capacitor or the parallel conductance. So here we put the equivalence of this conductance. Gp should be equals to 1 divided by Rp, right? So this conductance should, we can write down this conductance should be equals to the imaginary part j omega epsilon naught epsilon omega divided by d. Now we know that the value of this epsilon r should be equals to two part. That one is one part will be real part, another part will be an imaginary part. Now we can write down that x equals to y equals to j omega c plus gp. This one is the conductance part. So if we compare these two equations, then c equals to a epsilon r, and if we compare these two equations, that one is gp equals like this. We know that Gp is nothing but the conductance of this parallel resistance. So what will be the equals to Rp? So Rp equals to 1 by Gp. Very simple things. So what will be the input power? Input power, we know that P equals to Vi. So we can also write down that I equals to V divided by I, Yv. So that one will be Yv square. Just nothing but just put the values here. Okay. So that one is the input power. Now there will be the dielectric resonance. That one is the 1 by omega. Whenever omega equals to 1 by tau, then the energy story and the energy releasing, this one should be equals, and that one is known as dielectric resonance. So there is another term, that one is known as loss tangent or the loss factor, tan delta, or should be equals to epsilon r double prime divided by epsilon r single prime. So this one is defined as the loss of energy or the power loss per unit volume. So we know that the power, previously we have derived that power equals to V square divided by Rp or V square Y. That means the conductance, susceptance divided by V. So V equals to the area multiplied with the distance. So this one is a very simple formulas are here. So that one is the dielectric losses per unit volume. So this one is a graph for different frequencies. The That means the interfacial or the space charges, or the value of the epsilon, the curve of the epsilon r and the epsilon r double prime. Now here you will learn another mathematical problem. That one is the energy of the capacitor. So in the example number 7.5, you will learn the dielectric losses per unit capacitance and the loss angle delta. So W equals to the dielectric losses per capacitance. That means previously we have divided with the per unit volume. That means we divide by the volume, but here we will have to divide these things by the value of the capacitance. Okay, so very simple things is here. So this one is the ratio in with the dielectric current losses and the capacitor losses. Please try to solve the example number 7.6, 7.7. Okay. Now come to article number. So up to this one is the end of the article number 7.4.1. The next one is the 7.4.2. That means the Debye equations and the Kolkol plots and equivalent series circuit. We will not go in details of these things. And only things that you need to know, those who are doing your thesis on photonics or plasmonics or material science, this Debye equation is very important. And I think all of you know about this Kolkol plot from your electronics 2 course or from your control system course. So these are the so this one, the dielectric constant means the infinite, the epsilon r at infinite frequency. So we know that epsilon r equals to epsilon r prime single prime minus j epsilon r double prime. So there is nothing changed. Only the change is the parameter is changed with the epsilon r infinite. So there will be similarly there will be two terms. One will be real part, another will be imaginary part. Just separation of these two part. Then this one is the real part constant parameters, and that one is the imaginary part constant parameters. And this thing is derived from this half circle. And if we do the Kolkol plot, then we can also find out the values of these parameters. So you can also go through these things uh, and try to solve the example number 7.8. So this will be the end of the article number 7.4. So the next thing is that no need to go through article number 7.5 because these things are not included in our syllabus. So if you look at your syllabus, then in your syllabus, uh, we have already covered the Clausius Moncetti equations, spontaneous polarizations. That means we have learned different types of polarizations. Now today, what we have covered the frequency dependent dielectric constants, dielectric losses. And in the next lecture, we will learn the piezoelectricity. And this one will be the end of the dielectric properties of the material part. After that, we will learn the magnetic properties of the material. Okay. So, so this will be the end of our uh, today's lecture. And in the next lecture, we will start from article number maybe 7.8 or something like this, the piezoelectricity. And that one is very important, the piezoelectricity part. No, that one is article number 7.8. Yeah. So next class we will start from the piezoelectricity, ferroelectricity, and pyroelectricity. Okay. So now I will also upload this or recorded lecture along with the lecture of the board professors. That one is the lecture 21. Okay, and this one is this lecture. Okay, so hope to see you in the next problem solving class inshallah. Thank you.